Hi, and welcome to X Maths. My name's Lee, and it's great to be with you again today. And I'd like to just talk to you today a little bit about inverse functions and graphs. Now, the previous session we dealt with functions, so you're very clear on what a function is and how we can categorize them to various things. You're going to see this section is going to involve a lot of that as well. And of course, graphs, we've done revision of our grade 11, and you're going to meet one of your new graphs that you're doing this year as we go through this work. So let's just quickly recap a little bit on old work and remind you about a session we did where we did some revision of our grade 11 work. Right, if we have a look over here, you might remember we talked about reflections. And there were three kinds of reflections that we were working with. Let's just get three different axes up here quickly so we can just refresh our memories. And remember what we did is we talked about what happens if we reflect about the y-axis. And we would take a point, and I think if I remember rightly, the point we used was 5, 1. And we said, okay, if that is your original point and we're reflecting, it reflects this side. And A dashed would be the x value would change, but the y value would stay the same. And so it would become minus 5, 1. And we would get the rule that xy becomes minus x, y, if we're talking about symmetry about the y-axis. Right, now, if we have symmetry about the x-axis, we have our point A again, still the coordinate 5, 1. The point would be over here. So this is about the x-axis. And the rule that we'd be using is xy becomes, x wouldn't change, but the y would change to minus 1. Which is going to be that. And then the last one we did was when we talked about symmetry about the line y equals x, a reflection in that point. And if our A was over here at 5, 1, then if we reflected this side, A dashed would be 1, 5. And at that time, I remember saying to you that we know that if we're working with the inverse, we're actually just doing a reflection around the line y equals x. So in actual fact, this becomes yx. So actually what's happened is the x and the y interchange. Now this is the actual gist of the inverse as such, and this will always work no matter what. Now remember that it's very important to remember that an inverse is always symmetric about the line y equals x. So let's take something really basic, put the graph down, and let's see if we use this principle. We will in fact get a picture where the two graphs are symmetric about the line y equals x. Now at a simple graph, let's take a nice clear axis and let's think of something relatively easy to work with. Let's work with, say, y equals x plus 2. Very simple graph to draw. Now we know that if we're going to draw this graph, it's going to start by cutting the y-axis at 2, and the gradient is 1, so we make it 1 over 1, which is 1 up and 1 across. So 1 up, 1 across, there it is, and if we draw in our line along there, we can see our graph taking shape. So this is y equals x plus 2. Now remember I said to you earlier on that we're actually dealing with symmetry around the line y equals x. So let's put that line in. I need to just lift that up a little bit. Sort of wasn't quite straight on that. There you go. Right, so if my supposition is correct, that means if I go to this graph I had y equals x plus 2, and I want to find the inverse, then all I have to do is swap the x's and y's around. So in place of writing that y, I'm going to write an x, and in place of writing that x, I'm going to write a y. Everything else will stay the same. So now if I look at this, this is the equation of y equals x minus 2. So let's spin it around so it looks pretty normal. And we can see clearly here it's cutting at -2. Its gradient is 1 up, 1 across. And if we put that line in, let me make sure we use this thing so we can get a nice straight line. Okay, that's pretty much right. We can see that what we're looking at is a nice line that is reflected about my line y equals x. So yes, it would appear that it is as simple as interchanging our x's and y's. And that's working off the thing that is actually a reflection in the line y equals x. Now let's go and have a look at some typical exam questions and of course the complications that can result as a result of them wanting functions in particular will also come into what we're going to look at. Right, let's start with the first question. The first question says the inverse of a function is given as this. What is the function? Well, it doesn't matter which one we start with, whether we start with f and then go to f to the -1, which is, by the way we show our inverse notation, or does it matter if I go the other way around? So in other words, this way it worked like that, and does it matter if I start from this one and end up on that one? And the answer is no, there's actually absolutely no difference at all. It still involves a reflection around the line y equals x, and therefore it involves interchanging our x's and our y's. So now this is your inverse. Now what I would suggest you do is you work very clearly to help your examiner. So the inverse, f to the -1 of x, was 2x minus 4. So in simple terms, that would have been y equals 2x minus 4. Now, if I want the original, I know I must take this and I must interchange the x's and y's. So it's going to become x equals 2y minus 4, which means x plus 4 equals 2y, which means y is equal to a half x plus 2. And that means that f of x is a half x plus 2. Now, that is the original function, and the equation is finished. Of course, we are in a position to actually check this by drawing these two graphs and showing that if you looked at it, they would reflect around the line y equals x. I don't suggest you do that in an exam. This is only worth 3 marks. So you certainly don't want to waste a lot of time doing that. It makes much more sense to just be sure of what you're doing. But this, for the purposes of explanation, let us have a look at the graph. So I'll just get some more space down here, and let's get ourselves an axis. Oh dear, I seem to be in the habit of putting the wrong line thing on here. Let's just cut that out, go back here, and let's go to this graph here. Let's pop ourselves a y-axis and an x-axis. Just while we're here, let's talk for a little bit about this. You must always label your axes. You must always make sure you show the origin. And it's a good idea to have the arrows on the end of the axes. Just one side is fine. If you show 2 sides, it's not strictly correct, but it's not going to be marked wrong. Then, if we look at this first graph, this black graph, it tells me I'm cutting at -4. So I go down to -4 and I draw my y-intercept. My gradient is 2 over 1. So it's up to 1 to the right, up to 1 to the right. And so at this stage, I can draw this graph in relatively easily. Okay, and it looks like I need to shift it ever so slightly up. There you go. And we now have the graph of y equals 2x minus 4, which we know is the graph of the inverse. Now let's go and put the symmetry line in, which we'll know will be at 1, 1. So it's going to look like this. Okay. And now we can go and draw in this new graph, which is this one. Now this one tells me we're cutting at 2. So here we are at 2. And its gradient is a half. So that means 1 up and 2 to the right. So we're starting at 2. We're going 1 up and 2 to the right. So let's just get that. 2 to the right would be about here. Okay, as you can see, these are not very accurate graphs. It would be a good idea to plot these very carefully if you're going to look at this. Oh my gosh, look what I did there, nearly made a mistake. And I can see that I've actually made this line a little bit skew So let's just adjust it in properly. And if it's all drawn accurately, you'll see it would look like that, which is clear that we are right. So y equals a half x plus 2, and this is the line y equals x. And you can see if I folded on that line, it would superimpose on the black, and the blue would be the same graph. And the good news is that you don't have to do that. That was just to show you that if you want to check it, it's a very effective way to check it. It actually makes you feel more comfortable to know that you're definitely right. Okay, so I've made it very clear to the examiner that this is their inverse, this was the original. And notice the notation for the original, I just use f of x. For the inverse, I use f to the minus 1 of x. Now, be very careful about this notation. It's not this. That would be incorrect. Okay, I know it's confusing because you think to yourself, well, anything raised to the negative 1 is 1 over from exponents. But inverses, the notation we're using, is a function to the minus 1, which is not like our exponents. So just be aware of that and careful not to do that. Right, let's move to the next question. Now, in this question, you can see it says the sketch represents the graph of the parabola f, which intersects the x-axis at m0 and 2, 0. It is further given that the turning point of the parabola is 1/4 n. Points 0, 6 and k6 also lie on the curve. And you can have a look over here. That's got to do with symmetry, I'm sure. In fact, this whole question has to do with symmetry. Let's move up. All right, so on this graph, they've filled in the points we know, and we're ready to actually start looking at it. Now, in actual fact, there's very little work that has to happen here. It's all about understanding the properties of a parabola. And one of the important properties is that there's symmetry about its axis of symmetry. Now, if we look at this graph, we can see that this axis of symmetry is x equals 1/4, which means if I look here, this bit and this bit will be exactly the same length. Now, earlier on, they told me that this coordinate was an m0 and the other one was 2, 0. So we can go and put this in. That's 2, 0, and this one will be m0. But the question at the moment is actually concentrating on the value of k, which is this value here. Now, as I've said to you, this is actually the axis of symmetry, and it's happening at 1/4. So if I look this side, this is going to be 1/4 unit, and therefore this over here must also be 1/4 units. So in actual fact, 1/4 and 1/4 gives you 1/2, and so your k is 1/2. Right, so let's fill that in on our instructions here. So k is equal to 1/2, and the reason would be from symmetry. Right, the next question says find the value of m. Now, if we look at m, let's make it the green one, I think. This has to do with this x-intercept. And as I've pointed out to you earlier on, this distance here has to equal this distance here because that's the quality of the axis of symmetry. So 1/4 to 2 is actually 1 3/4 units, which means this must also be 1 3/4. So we're going to take 1/4 and we're going to subtract 1 3/4. If we do that, we're going to get minus 1 1/2. So I know this coordinate is minus 1 1/2, 0. Right, let's go down to where we have to fill it in. And I've already gone and happily forgotten what I said it was. It was minus 1 1/2. So let's write it in. So it would be minus 1 1/2. And again, it's by symmetry. And you may notice that these are only worth 1 mark each. So they're not expecting huge amounts of calculations. If something's worth 1 mark, then simply just means it's something you can write down, literally just thinking about it or seeing it on the actual graph. Right, C says, find the value of n, show all working details. So let's go back here. Well, to get n, we need to know the y value of the turning point. Now, at the moment, we don't know the equation of this particular parabola, but we are in a position to actually do that, because all we need to be able to find the equation of a parabola is know the x-intercepts and one other point, or know the turning point and one other point. Now the turning point is where our missing element is, so we can't use that. But we certainly can use finding our equation given the two x-intercepts. So let's have a look at it. We've got y equals, and if we've got the x-intercepts, we can go x minus x1, x minus x2. So it's y equals a. If I have a look here, this will be x minus 1.5, so it's plus 3 over 2. And this one over here would be x minus 2. We now need to know one other point, and we actually have got 2 points. We can use this one or this one. I personally am going to use this one. I think it's easier to work with 0, 6. So what I'm going to do is I'm going to substitute 0, 6 in there so that I can solve for my a. So 6 is equal to a. If I put 0 for x, I'm just going to have 3 over 2. And if I put 0 for that x, I'm just going to have minus 2. Now looking at it, that 2 divides into there once. So I've got 6 is equal to minus 3a. And so a is equal to minus 2. So my equation is y equals minus 2, x plus 3 over 2, x minus 2. Right, now we're going to multiply this out. So y is equal to minus 2. If we're going to times the first there, we're going to get x squared. If we times our outers, we're going to get minus 2x. Our inners are going to be plus 3 over 2x. And our lasts are going to be minus 3. Tidying that up, I've got minus 2x squared. Timesing here, I'm going to get it's plus 4x. And that times that's going to be minus 3x. And that times that is plus 6. So this is equal to minus 2x squared plus x plus 6. And there we have the equation of this parabola. So it's y equals minus 2x squared plus x plus 6. Now, if I want to find n, all it would require is me substituting the quarter in for every single x. So let's go down to where the question is. Now we've got the equation. I must just keep the equation handy so we can refer back to it. The equation is y equals minus 2x squared plus x plus 6. Okay, now as we have discussed, we know we're going to substitute in x equals a quarter because that's what the x value is there. So we're going to substitute x equals a quarter. Now doing that, we've got y equals minus 2, a quarter squared plus a quarter plus 6, which means we have y equals minus 2. Now a quarter squared is 1/16 plus a quarter plus 6. Which means we have y equals minus 1/8 plus a quarter plus 6. Now that means that y is equal to, and let's put the whole thing over 8, it'll be minus 1 plus 2. Remember that's over 1. 1 goes into the 8 times. 8 sixes are, or is, 48. Adding that, I'm going to get 49 over 8. So that's my y value of the turning point. So I have a quarter with 49/8, which means now at this stage I can say n equals 49 over 8. Now so far this is like any question we would have got in grade 11. No difference at all, and you can see it's relatively straightforward. We're comfortable with this, we've been doing this for a while. It's not strange. Now the next question is the first one that introduces the whole function concept. It says the restriction on the range so that the inverse of f is a function. Well, let's go back up to this actual graph. And what I'm going to do is I'm just going to clean it up a little bit because it's getting a little bit busy. And let's just put in some of these important points we have found. In fact, we don't even have to. We knew that this was 2 naught, was it? Yeah. Now, if we're using the function concept and the inverse concept, remember we talked about how this was in fact just a swapping of your x and y's. Now we found n to be, let's just go and get that, 49/8. Now if we're going to do the inverse, all we're going to do is we're going to swap around our x's and our y's. So where we had an axis of symmetry of x equals a quarter, we will now have an axis of symmetry of y equals a quarter, like that. Then our turning point, which was a quarter 49/8, now becomes 49/8 a quarter. The intercept, which was 2, 0, is now 0, 2. So it's more or less over here somewhere. Of course, this is not drawn to scale. And this was cutting at 6, 0, 0.6 rather. It will now cut at 6, 0. So it'll be along here somewhere, 6, 0. So what's happening to this graph is it sort of looks like this. Of course, the scale is a little skewed. Now, can you see that the black graph was actually a function? Remember how we tested for it? We took a vertical line and we slid it through the area. So we take it along like this, and we see it only crosses the black graph once. But do you see if I go to the blue graph, it's no longer a function. You can see now the x's are repeating nearly all the way through the graph. Over here it's just once, and then over here it's nothing. But other than that, it repeats at least twice. So this is clearly not a function. Now the question is saying to me, how do we make sure it's a function? Well, we have to restrict the domain. Now if we look at this, if I choose to work with, say, this half of the graph only, unfortunately this has decided to go straight on me, so let's use another color rather. Let's use the green one. So I decide to work just with this part. Now remember, the symmetry is about the line y equals x. So looking at it like that, I would be talking about this bit here. And I think you can see, if you use your imagination a bit on the scale, that if we had to put in the line y equals x on the scale, those two bits would coincide. Likewise, the black part that's left of the original with the blue part of the inverse will also do just that. So we can see that that's how we would get it to be. So we always use the turning point as the cutoff point to make sure that our inverse happens. So going back to the question, it says the restriction on the range so that the inverse of f is a function. Now on f, the restriction would be either x greater than equal to a quarter or x smaller than equal to a quarter. And you could have even gone with x greater than a quarter or x smaller than a quarter. Now, the range of the inverse is actually the domain of the original. So for f to the minus 1, and let's use a different color so we don't get confused, y would be greater than equal to 1/4, or y would be smaller than equal to 1/4, or y would be greater than a quarter, or y would be less than a quarter. So what we do is we always use our turning point as our way to make sure that whatever's the inverse is going to be the case. So let's have a look and see what I mean by that. Let's look at another example of it. Supposing I have this graph. And let's move this axis of symmetry over that end, and let's put a graph in here. Let's suppose it looks like this. And this coordinate is -5, 10. And I want to restrict the domain of f. So the domain of f, if I have to restrict it, must be either to the left or the right of the turning point. Now it really doesn't matter, they might have given you more details, but usually they don't. They leave it to you to choose. And so what we could say is that the x would be greater than -5 or greater than equal to -5, and then I would be talking about just this bit. Now if you're looking at this part, you definitely see it as a function. If I slid my vertical line through this, you would see it quite clearly. Let's put it down here. Let's pick it up and show you. Yeah, it's a function as well. But over here, if I'm looking at the blue, it's actually a 1-to-1 function. But if I look at the whole graph, it's a many-to-1 function. Now, if it's a many-to-1, let's think about this logically. you can see why we could have a little bit of a problem. If f is a many to 1, and as we said, an inverse is swapping the x's and y's, do you agree with me it now becomes a 1 to many, which is clearly not a function. This one is a function. So it makes perfect sense why, when I do the inverse of a parabola, that doesn't work. So what we do is we restrict the domain to make sure that our function, our original, is 1 to 1. In other words, if I go over here and I take away this bit, which is what I'm actually doing, you can see if I look at this blue graph now, it's clearly a 1 to 1 function. And so if I make it an inverse, so if I was going to do the opposite of this thing, it would sort of become 10, negative 5, so it would be over here somewhere. And it would sort of look, let's make it a green graph. It would look like that. Can you see that this green graph is also a 1 to 1 function? And of course that makes sense, because if we're interchanging these guys, 1 to 1, 1 to 1 still makes it a function. So this is a very common question, and you'll often find them asking it in almost an algebraic form. So let me show you what I mean by that. I could say to you, let's make the black pen, determine the domain of f that ensures f to the minus 1 is a function if f of x equals 2x plus 1 squared minus 2. Now, if we know anything at all about functions, we're not thrown by this at all, because we know we can actually draw a sort of sketch of this and look at it. So let's get a sort of sketch going. We know immediately just by looking at this that the turning point will be minus 1, minus 2. So minus 1, minus 2 like this. And if we look at it, it's a smiling graph, so it's going to sort of look like this. Remember, I said to you the most important thing to know about is actually the turning point. So here we have it. If I put my axis of symmetry in, you can clearly see that if I'm interested in getting a thing, I could take this side or the black side. Now, since I took the right side last time, let's take the left side this time. So I could say if x is an element, now what do we know? We know it's everything from minus infinity to minus 1. And again, we can choose to include it or not include it. Let's include it this time. Or I could have just gone x is smaller than or equal to minus 1. Then f to the minus 1 is a function. Now, if they asked you to explain why that is, it would be easy for you, because all you would do is you'd say, well, by restricting my domain of f, I made it that it was a 1-to-1 function. And if I'm dealing with an inverse, the x and y are swapping around. So instead of being 1-to-1, it's now 1-to-1, which is exactly the same thing, and therefore a function. So relatively easy and straightforward. Right, let's look at the next question. The next question says the graph of function g is shown below. Let's have a look at this graph. Okay, it's got some interesting twists and turns. It comes along as a straight line here, and then it's kind of a curve till it reaches here. So it doesn't include this one. It does include that one. And we can actually find coordinates here. That's 2, 4, 5, 6. So it's 6 for x and 2, 4 for y. And this one over here would be minus 1, minus 3. Although it's not included, that would be its coordinate. And we know that this is 0, 0. Okay, so we mark the origin in there. Now it says, give the domain and range of the function. Now remember, the domain and range we discussed last lesson. Domain is the possible x values, and the range is the possible y values. We talked about alphabetically x comes before y, alphabetically d comes before r. Right, so if we look at this now, we can look at this and we can say, what is the possible domain? Well, do you agree with me? X would be an element of. Now, I'm starting from minus 1, but I'm not including minus 1. So it would be round bracket minus 1 to this value, which is the y value, which is 6, which is included as 6. Then the y. Y is an element of, and now we're looking at the y value. So now I'm highlighting these and that. So what is the smallest possible y value? Well, I can see the smallest possible y value is -3. And again, because that's a round dot, I don't include that. And the highest possible value for y is 4, and I do include that. So giving the domain and range of that function relatively easy if we're using our graph. Let's do a little bit of tidying up here. I'd actually like to leave that coordinate up there because I'm sure it'll be useful just now. So this was -1, -3, and this is 6, 4. All right, it says draw a neat sketch graph of the inverse function of g. Now, you might have noticed when I was looking at the inverses earlier on, I wasn't finding the equation and then working. I was just saying, well, look, I know that all the coordinates will swap around. So that's exactly what I'm going to do. 0, 0 will still stay at 0, 0, but the coordinate -1, -3 will now become -3, -1. So -3, -1, here it is. And I know it's not going to be included because it wasn't included in that one. Likewise, this one here, 6, 4, is going to become 4, 6. So 4 and 6 up there, and that one will be included. So now I know it'll look like that, and this bit will look like that. That's quite an attractive little shape. You can see it looking quite agreeable. Now, if you can imagine, there's a line, y equals x going through here. Just need to straighten it up a bit. Flatten it down. And that's a pretty good representation. And you can see that that is clearly, if this one was the original, this is now the inverse. Can you see that we've used this line to fold over? And I think you can see it's a rather attractive little, like fishy shaped thing. Now, it says explain why this inverse is a function. Well, let's first of all make sure, is it a function? Let's take our test, which is our vertical line test. Let's get ourselves a line going. And let's search the graph. Now, we're looking at the blue. Do you agree with me? It's got one cut, one cut, one cut, one cut, one cut, one cut, one cut. Yes, most definitely it is. Now, why is it also a function? Well, remember what we've just been talking about. We've just said we're going to look at the original. So if I look at the original, we know that it was a function and it was a one-to-one. How can I say that? Well, if I go back here and I use my vertical and horizontal line check and I slide this horizontal line through the black graph, do you agree with me? It only crosses once at any one point. So therefore, this is a one-to-one. So that means that the new one, because it's an inverse, those will interchange. It'll also be a function because it's also one-to-one. So that explains why the inverse is a function. And as we pointed out earlier on, that if the original had been many to one, and then we found the inverse, it would be one to many. And that would not be a function. And that's why we need to know to restrict our domain. Right, let's move on to the next question. All right, it says the graph of g of x equals 2 over x and f of x equals minus 2x squared. They are drawn on the same set of axes below. Now, those of you who watched our last session will be thinking, hang on a moment, this looks identical to a problem we did. And the answer is it certainly is identical. This is y equals minus 2x squared, and this is y equals 2 over x. So I didn't waste time going back to drawing this and sorting it all out because we did that in the last lesson. All I'm going to do now is concentrate on the questions that followed after that concerning inverses, etc. Now it says there, write the equation of f to the minus 1 in its simplest form. Now f is this parabola. Right, let's go to a fresh page where we've got some room to work, and let's see how this works. Right, they gave me the equation y equals minus 2x squared, and that was my original f. I now want to find the inverse of f, and to do that, I know I'm going to swap around my x's and y's. So f to the minus 1, notice how I'm showing the examiner how I'm doing this, is going to be x equals minus 2y squared. Now, it's not acceptable to leave the equation like that. We always have to work it into y form, and even more so because this question asked you to put it into y form. So we definitely don't want to leave it there. So let's have a look at what we're doing here. We're going to say that x over minus 2 is equal to y squared. And now what we need to do is get the y on its own. So to do that, we're going to say y is equal to plus or minus the square root of minus x over 2. All right, going back to our previous page and filling in what we found, we've got it y is equal to plus or minus the root of x over minus 2, or minus 2 over root x. Now, just by the way, it would depend which half of the parabola we're working with. If we're working with this part, one of these would apply, and if we work with this part, one of those will apply. Now it says restrict the domain of f so that f to the minus 1 is a function. Now remember, I said to you, whenever we have to restrict the domain of a parabola, the easiest way is to work with a turning point. So if we go to this fresh page, that was question A. B, we know that the turning point would be 0, 0. So it would be all right to say x is an element of minus infinity to 0, or we could have even just written x smaller than 0, or we could have introduced the square bracket and made it equal to as well. I think for the purposes of this, let's make it always the equal to one, although, as I say, they wouldn't mark you wrong if you did the other way. Right, so let's leave it like that. And as I say, simple. Or we could have gone along and said x is greater than equal to 0. It would be your choice, and they would have to mark both options correct. So back to the question. Right, the next one says, write down the equation of g to the minus 1 in the form of y equals. So again, they're forcing you to go to the y equals format. So let's have a look at that. That's option C. G was the equation 2 over x. So G was y equals 2 over x. Now, to get the inverse, we would swap the x's and y's. So we would get x is equal to 2 over y for g to the minus 1. Now, looking at that, that means that xy equals 2, which means y is equal to 2 over x. Okay, look at that. It's exactly the same graph. Now, obviously, there must be some reason why that's working out like that. Let's go back to the questions. So this is going to be y equals 2 over x. And it says, what do you notice about g and g to the minus 1? Now, hopefully you realize that if it has the same equation, it's the same graph. Now, remember what we talked about. We talked about the fact that this graph has symmetry. And in fact, I remember us looking at those lines. And in fact, we looked at one where we actually change it around. Now remember, that's the reflection line we're going to use. So this is the y equals x line. And you can see that this one will coincide on this one, and this one will coincide on this one. And so yes, the graph is actually not changing at all, which makes perfect sense. So what you notice is the graph of g and g to the minus 1 is exactly the same graph. So here we go. G and g to the minus 1 are the same function. And are you happy with me using the word function? I think we've established very clearly at this stage that hyperbolas are functions. They are actually one-to-one functions, which makes sense then that their inverse is also one-to-one. So we've established that that's the case, and the reason would be that there is symmetry about y equals x. Okay, good. So now let's go and look at the next question. Let's go past that work. And you'll see they've now given me quite an interesting little graph. They say, study the sketch below and then answer the questions that follow. Let's bring it up. Okay, the first question says, describe the domain of f. Now remember, we talked about domain being x values. So when I look at this graph, let's get a highlighter. I must talk about the first x value I get all the way through to the last one. Now if we look over here, there's nothing drawn there. There's no like big open circle. So what we assume in a case like that is that this is in fact a solid point. So the domain of this would be x as an element of -3 to 4. Nice and straightforward, no problem. Now the next question says sketch the inverse. Now again, I'm not going to worry working out the equation, because with what I know, I have enough information to swap around my x's and y's. So going over here, instead of having -3 on the x-axis, I can have -3 on the y-axis. I might have to just extend this out a little bit, so let's do that. In fact, I think I should use the solid line. Okay, back to the graph, and there's the -3. And then this is 4 on the y-axis, so it's going to be 4 on the x-axis. Then there's a kind of parabola here, where she'll cut at 2 over here. And then this point is 4, 4, which will be 4, 4. So we can actually draw this very, very easily, as you can see. You can see that art was never my strong point, and so there's some interesting little curves and things going on, and this was a dotted line across to 4. Okay, a very skew one, but anyhow it'll do just fine. So this would be f, it does help if one goes back to the pen, this would be f to the -1. So sketching the graph, no problem, it's just a matter of interchanging our x and y values. Right, now it says, is f to the -1 a function or a non-function? Explain. Right, so remember how we decide that? We take our vertical line and we start by sliding it through the purple graph. Now immediately, as soon as I do that, we can see clearly this is not a function, because if you look over here, here's a point, here's a point, and here's a point. So clearly there's more than one x value with 3 different y values. And there might even be more like that. In fact, there are more like that. So definitely we know for a fact that that's not a function. All right, let's just put this graph back here. So we've got it for future reference. And we can happily take this line off the graph. Right, so it's definitely a non-function. Okay, let's bring this up a little bit. So it's a non-function. Now to explain it, we would say what kind of animal it is. Now remember, we said if it's a non-function, the last one will always be many. Now we have to decide the x value, and to do that we use a horizontal line. So we put it like that, and we again slide it. Now if I slide it, it's cutting once, cutting once, cutting once, cutting once, all the way through. So we can see that for the x value, it is going to be a 1. So let's just rewrite this a little bit closer this side. So it's going to be 1 too many. Right, now in this part D, it says for the straight line f, when x is an element from -3 to 0, write down the equation of f to the -1 of x in the form y equals. Now remember, I said to you, it's quite important we know to write it in y form. They don't always ask it, but most times they do. So what are we interested in? We're interested only in this portion of the graph, and in particular, this line. So we need to go and find the equation. Now to find the equation of this line, it's a straight line passing through the point -3, 0 and the point 0, 4. Now we can find the gradient using y2 minus y1 over x2 minus x1, and so we could say it's 4 minus 0 over 0 minus -3, which means we're looking at a gradient of 4/3. Remember, I said to you, it's always important to think to yourself, is this answer realistic? And what are we finding? We're finding the gradient is positive. Now, if I look at this graph, is this gradient positive? Yes, it is. So it makes perfect sense. So it's y equals mx plus c, and therefore it's y equals 4/3 x plus c. Remember, c is the y-intercept, so it'll be y equals 4/3 x plus 4. All right, there was another way we could have done this particular question. We could have started from the fact that we know the c value is 4. So we would have y equals mx plus 4. we would then substitute another point. So the other point is this point, minus 3, 0. Doing that, we're going to get 0 is equal to m times minus 3 plus 4. And if we look at that, we're going to say 3m equals 4. So m is 4/3. So your equation is y equals 4/3 x plus 4. Now, we've got the equation of f, so let's go down to it and put it in there because we need to know it for now. So d, we know it's going to be y equals 4/3 x plus 4. And remember, that is for the interval x, an element of minus 3 to 0. So we've got this part. We now must do the actual question, which says write down the equation of f to the minus 1. So remember, we said to you that this was your original. In fact, let's keep it in that color for now. And we now want to go to the inverse, which means we go along to this and we change our x's and y's around. So we're going to have x equals 4/3 y plus 4. But it doesn't just stop here. It also applies here. So this becomes y an element of minus 3 to 0. Because obviously, if we're going to change x's and y's, it affects your restriction as well. So instead of x being restricted over the interval minus 3 to 0, y will be restricted over the interval minus 3 to 0. Right, now this is not good enough because the question said write it in y form. So to do that, we times through by 3. So 3x is equal to 4y plus 12. And therefore, 4y is equal to 3x minus 12, which means y is going to be 3/4 x minus 12 over 4, which is 3. And that gives me the correct equation with that restriction. So that would be the answer we're looking for, that with this new restriction here. All right, so relatively straightforward. We're working over a limited interval. And now they're going to ask me something else about another part of the graph. But just be careful to not always think once they start with inverses, that's all they're working with. They can bring in any of our reflections or rotations at any time. And this is what the next question is about. So let's read it. It says if the equation of f when x is between 0 and 4 is given by that. Notice that. Is it feasible what they're saying? I think it is, because you can see that that would clearly not have shifted off the axis and it would be looking sort of like that. So we want it between 0 and 4. There's our 4, there's our 0. And they want you to write down the equation of g of x, which is the reflection of f about the x-axis. So we're not talking about inverses now, but rather about reflections about the x-axis. Let's get ourselves a clean sheet here, and let's look at the question. Right, so if we're looking at this equation of f, it's equal to x minus 2 all squared plus 0. Do you agree with me that that plus 0 is not necessary at all? It is perfectly acceptable to write this equation like that, because by writing plus 0, all you're doing is you're telling me there is no shift upwards or downwards. So in this case, I would just happily leave off that 0 because it really serves no purpose to have it there at all. Right, now they want me to find g. So let's swap pens. We want g of x, which is the reflection about the x-axis. Do you remember the rule we quickly summarized at the beginning of this session? We talked about if it's about the x-axis, the sign of y changes. So that's what will happen. The xy will become x, negative y. So if we go to this purple one that we've got up here, this y equals x minus 2 all squared, and we're now going to use that rule. We're going to say minus y is equal to x minus 2 all squared. Of course, that's not y form, so we bring the negative over, and we get that. Now the question is, there was a restriction on our domain. They said between 0 and 4. Now, will this change in any way? Well, no, because we're reflecting about the axis, and only the sign of y is changing. So that means that restriction of x an element of 0 to 4 will happen the same way for this particular graph. So this restriction would still be x an element of 0 to 4. Now, of course, we could work with any of the reflections or any of the rotations along the same sort of line, and we'd have to just watch that our restriction on our domain does not get affected by these mirrors. But anyhow, I'm sure that's a clear enough picture of what we're looking at here. And let's just go back to this thing here and think about it. Remember, we just talked about that, and it makes perfect sense that this is what they'd be talking about, because it would be reflected about this x-axis. So again, a good thing to do is to always think to yourself, is my answer feasible? Does it look like it could be correct? Because that helps you to keep a check on whether you're going wrong or not. Right, let's look at the next question. It says, use the given sketch of the function k to answer the questions below. Now, this is quite an interesting sketch. I'm sure you probably have never seen one like this before. And really, if you look at it, it's no different to the ones we've been doing already. It's just something unusual. They're not using a recognized graph that we usually work with all the time. This is actually called a step function. Now, I'm using the word step function. How can I safely do that? Well, the first thing we do is we would take our vertical line and we would check. And as we go along here, do you agree with me that the x's are not repeating? Even over here, it's not included there, but it is included there. Over here, not included there, but is included there. So there's no problem. There's no repetition on the x. Now, if we look at the y value, let's take our horizontal line. Well, that's a different issue altogether. Because as I slide it down and I get it there, oh my gosh, all of those repeat. Likewise up here, all of those repeat. And likewise over here, all of those repeat. So in actual fact, this is definitely a function, but it's not a one-to-one function. Remember how we said we would read it? We would look first of all at the y's, and looking at the y's, we can see that there are many y's to 1x. So it's a many to 1. Now, why does k represent a function? Well, the y is because the x values do not repeat. All right, let's carry on with the question. It says, if k is 1-to-1 or many-to-1, is it 1-to-1 or many-to-1? We've already decided that. We've decided it's many. Decided to pick up the whole thing instead of just the part of it. It's many-to-1. Explain. Well, the y's are repeating, but the x's are not. Y values repeating. X values are not, therefore many to 1. Okay, quite important. Now, the next question says, what is the range of the inverse of k? Now, remember I said to you that we're swapping x's and y's around. So if I'm asking you the range of k to the minus 1, it's equivalent to asking you the domain of k. Now, if I'm looking at the domain of k, here we have it. Domain is possible x values. So if I start over here, can I have 0? No, because there's an open point there. So we're going to start at 0. And I can keep going. At this point 2, can I have 2? Yes, it's true for this one. Not true for that one, but it's true for this one. And along I go, and eventually I get over to 3. And 3 I can have, not over here, and 4 I can have. So it's actually going to be from 0 to 4 inclusive. Now that was the domain of k, but we want the range of k to the minus 1. So therefore it's going to be one element of that. It's the range of k to the minus 1. Notice I didn't worry about whether I actually had the domain or the x values or anything. I didn't redraw it. I didn't do anything. I just used my understanding of how an inverse works. And it's fine if you want to go the long way and actually go and draw it and then get the answer. Let's just write it out a little bit more neatly. So it's going to be y, an element of not including 0 to 4 inclusive. Now it says, will k to the minus 1 represent a function? Explain. Now clearly it won't do that. Remember over here we had many to 1. So the inverse will be 1 too many. So therefore, a non-function. Right. Now, let's go back to the graph and let's see if this is true if we actually did the drawing of the graph. And I think let's get hold of that predictor pen that makes it now straight lines. So instead of it looking like this, it would start over here and it would go up to 2. Then it would start over here and it would go up to 3. Then it would start over here and it would go up to 4. We know that this would not be included. That would be included, not included, included, not included, included. You can see that's quite beautiful. Look at all that lovely design that's coming out there. I get quite excited when I see something as nice as that coming out. And you can see that if I slid my vertical lines through this, I would have a problem as soon as I try to move it around the blues. So as soon as I put it there, look at that. It's lots of opportunities for the X to repeat. A little further on, same there, and same there. So it's clearly not a function, but we can see that very easily from looking at the actual equation. The fact that we knew it was many to 1, and now it becomes 1 to many, therefore a non-function. So an explanation would be, because the x's and y's are swapping around, a many to 1 will become a 1 to many, which is a non-function. So we can write that out so that they can see that clearly. K was a function, many to 1. So k to the minus 1 is 1 to many, and therefore not a function. X value repeats. And I'm sure it's very clear for 2 marks. That's more than an adequate explanation. Right, so now what are we going to do next? We're going to touch a little bit on a section that is extremely important. It used to be a huge portion of the previous syllabus. The good news is it is no longer such a huge portion, but it is still an important concept. We're going to start working with inverses of exponential graphs, and this is the first introduction you have to new graphs. So let's get ourselves a blank page and let's just have a look at this and talk about it a bit. Now, if we're looking back to when we were working in grade 11 and we say I had to draw this graph, there was no real problem. We went along and we put our axes together. There it is. And to actually sketch it was no problem. We went and found a few values. We said, all right, if x is minus 1 or 0 or 1, it'll give us an idea how it looks. So it becomes y equals 2 to the minus 1, which is the same as saying a half. And then it would become y equals 2 to the 0, which is the same as saying 1. And then it would become y equals 2 to the 1, which is the same as saying 2. We would plot these points. Let's just get ourselves a fair looking axis. So we plot minus 1 against a half, 0 against 1, and 1 against 2. And this is how our graph would look. And it's called an exponential function. It's y equals 2 to the x. Remember to mark x and y and the origin. Now remember, I said to you that an inverse has to do with a reflection in the line y equals x. So let's put the line y equals x in, and let's go and plot this. So instead of cutting here, it'll cut there. Instead of having negative 1 1/2, we're going to have a half negative 1. Instead of having 1 2, we're going to have 2 1. So this is how this graph looks. And that would be the inverse. Just before we move off that, we know that this would be an asymptote for the pink one, and likewise this would be an asymptote for the blue one. So even the asymptotes have swapped around, whereas before it was the x-axis, it's now the y-axis. Makes perfect sense. All right, so let's get rid of this bit. And let's go to the actual question. Now, we're starting with y equals 2 to the x. If we go into the inverse, we're looking at x equals 2 to the y. Now that's not a problem, but now the problem comes in if I say to you, you must write this in y form. Because how on earth do you do that? You've got no idea at this stage how to do that. So what I need to do is stop for a little bit and define a new function called the log function, which is basically the inverse function of an exponential graph. And it's the first of your graphs you do in Metric. Good news for you is there's only the logarithm and the cubic function that you have to still do. Most of them have been done in grade 10 and 11. So let's have a look at what this means. To do this, I'm going to stop for a few seconds and just do a definition with you. In fact, let's rather bring it up a little bit and put the definition over here. The definition goes as follows. It says, if I have log to the base a of b equals c, then it becomes a to the c equals b. In other words, it's possible to change this into this. Okay, let's talk about what I'm saying here. So if I've got y equals 2 to the x, I can go log to the base 2, because the a is the base, of y, because y is the number, equals x. Now I'm sure you can see that if I swap them around now, I'll have it in y form. And there it is. So relatively easy to do it that way. It certainly makes life a little bit easier for us. Now I'm going to stop and spend some real quality time here, because we need to understand the definition of this log, and we're going to use the calculator to actually do this so we can relate to what we know. Right, let's have a look at what happens if we use the calculator. Before I do that, I'm just going to jot down an example. Let's take 3 squared equals 9. We know that's true. And if we're going to use that definition I was discussing, that if we have a to the b equals c, then according to my definition, it becomes log to the base a of c equals b. So in other words, this will become log to the base 3 of 9 equals 2. So let's pull up our calculator and see if that's correct. Here we have it. Well, we know that that's true. Now what we're going to do is we're going to use this calculator key that looks like that, because we can input the base and everything. We're saying the base is 3. We're saying the answer was 9. What was the exponent? Well, the exponent was 2, which is precisely what we knew anyhow. So let's put it this way. If we have a base to an exponent equals a number, then we know that log to the base of the number equals the exponent. So log is actually just the exponent part of a power. And so it becomes really very easy to think like that. So let's just check one more to make sure we are committed. Let's take 10 cubed equals 1,000. We know that that's true. So we're going to go log. What was the base of this expression? The base of this expression was 10. What is the number? The number is 1,000. And the exponent is 3. So let's pull the calculator up and see if that's true. It's clear. We're going to go to this button here again. Our base is going to be 10. And we're going to put in here 1,000. And yes, you can see that's true. So now that's easy while we're looking at examples that we know and we understand. Just one thing I must stress here is that it's very, very, very important that your base is tucked under the tail of the G. If it's not, it can be very confusing as to what you're doing. Right, let's take some that you're not familiar with. Let's take 2 to the power 0,5. Okay, now that's something you wouldn't probably know off by heart. And let's pull the calculator up and work that out. Okay, so that's 2 to the power 0.5. And we're going to get 1.414, etc. So it is 1.414, etc. Now, if it's true, I can go log to the base 2 of this 1.414, etc., and get the answer 0,5. Let's see if that's true. Now, you know how this calculator works. We're going to go straight to this button. We know our base is going to be 2, and we know over here we must put our answer. Now, notice I didn't go 1.414 because that was just an approximate value of it. I used the actual answer on the calculator. Right, once I press equals, there you can see a half, which if you make a decimal is going to be 0.5. All right, so it does work perfectly all right. We get the answer we should get. Just a few more things concerning this definition, and that is if I just write the log of 4 with nothing here, if you like, the default is that we are working with base 10. So if I go back to my calculator, you'll see that there's a button over there that just has log. Now if I use that button, I'm using base 10. So if I went log 1,000, because that's what I was working with just now, there's your answer 3. So that's working with the default, if you like, of that. So nothing written, we assume base 10. Now I'm not going to go much further than this on logs. We will spend some more time on them at a later stage. They are important. You have seen them in the matric finance. If you've done matric finance, you use it quite a lot. And you will see it when we get to those sections and we go through them. I think we will have probably gone through it by now. But let's have a quick look and see how this now works for us. Let's get the new question. Right, it says, sketch the graph of y equals f of x equals 3 to the x. Now, I must be honest and say that I'm not wild about this kind of notation. I personally would rather have called it f of x equals 3 to the x. Now, that is a straightforward graph that we drew last year, so let's quickly knock it up. Notice, please, that in actual fact they are being very specific. They say label at least 2 defining points clearly. Now, what do they mean by defining points? That they would mean points that are unique to this particular graph. So plotting the point 0, 1 won't help because 0, 1 belongs to any graph of the form a to the x. So it won't help you to plot that point, but any other point will be good. So that's what we're going to do. So let's have a look. If we go over here, if I take x equals minus 1, I can say I'll get 3 to the minus 1, which is 1/3. So I would plot the point negative 1, 1/3, which is defining. We know it'll always go through 1, and at 1 we will get 3, which will be here, 1, 3. So that gives me my graph, and I've got at least 2 defining points. If I show more, that's also fine. Now it says determine the inverse of f and write it in this form. So right, let's go to the bottom of this page and let's work with it. We know that we've got y equals 3 to the x. We are asked for the inverse, so the inverse, that was f, the inverse would be x equals 3 to the y. The problem is we can't write it in y form, so we need to use our definition that c equals a to the b implies log to the base a of c equals b. So y equals log to the base 3 of x. So that then gives me that equation, which I'm going to write in here, log to the base 3 of x. Notice I'm making it very clear that that is the base and not part of this top section. Right, the next question says, sketch the graph of f to the minus 1 on the same set of axes as f. Label at least 2 defining points clearly. Now, obviously, you can go and work out new defining points, but why do that? Just use the ones you found for 3 to the x and turn them around. So let's go here. We know that that'll be 1 and that'll be 1. That's not defining. But this one, 1/3 with negative 1 is. And instead of 1, 3, we can plot 3, 1, which is over here. And we can see here is our function f to the minus 1. So that was f, that's f to the minus 1. The 2 defining points are there, so it's very clear to them what you're doing. Now it says, is f to the minus 1 a function? Give a reason for your answer. Now let's go back to the original f. And if we look at f, if we're looking horizontally, first of all, let's look horizontally. Do you agree with me that every y value will be unique? So it's going to be f, a 1, And if we look at the x values, it's also going to be 1, so it's 1 to 1, and it's a function. So the inverse will also be 1 to 1, because these will interchange, and therefore a function. So I'm telling them that, and the conclusion, I think, is very clear for your 2 marks. Right, let's have a look at E now, where it tells me g of x is equal to the f of x minus 4 minus 3. And the first question they ask me is to describe the transformation of f to g. Now, if we look at f, what are we doing? We are moving 4 units. Now, it's a negative 4, so we're going to move 4 units in the opposite direction to the sign, so to the right. And this is minus 3, 3 units down. So we can say f moves 4 units to the right and 3 units down. And that would give me the answer for number 1. Right, number 2 says, sketch the graph of G and show any new asymptotes and label at least 2 defining points clearly. Now, the easiest way to do that is to basically use the work we have done originally for f. What did we know for f? We knew that our defining point was at minus 1 1/3. We knew that there was a point at 1, and we knew there was a point at 1 3. And all we're going to do is we're going to use this transformation to help ourselves out. So instead of being at minus 1 1/3, it tells me I must move it 4 units to the right and 3 units down. So we need a little bit more space, I think, over here. Let's just drag this axis down a little bit up. Okay, so if that's the case, instead of here, we're going to move it 4 units to the right, so it'll go over here, and 3 units down. So it's going to be 1, 2, 3, it'll be about here. The coordinate would be 3, and if I'm going to move this down 3 units, it was 1/3, so it'll be actually 2 and 2/3. Right, then once we're here, this point is also going to move 4 this way and 3 down. So this coordinate, instead of being 0, 1, will become 4, negative 2. And this point, which was 1, 3, is going to again move 4 units right. So from there, it's going to become 5. That's 4, 5. And it's going to move 3 down, so it's going to be over here at 5, 0. So we have the graph looking like that. Of course, the asymptote has changed, and that's what they sort of preempted for us. We know it was here at 0, but it's now shifted down 3 units. So this one will happen at x equals minus 3. Okay, now there's only one asymptote to worry about on this particular graph. So we're looking good, and that's the end of that question. Not so bad. Let's move across now and see what the next question brings. And the only difference between this question and the question before is this time we're starting from the log graph. Now you might notice that the log graph is looking like this. Remember, the original would have looked like that. And remember, the reflection is about the line y equals x. So it makes sense it looks like that. We will spend some time looking at the sketches of that when we get to graphs. Logs rather. And then we'll be able to see how that works. Now, here they say to me, we're given this equation, and they ask me to find the value of A if Q is the point 8, 3/2. Now, it's always better to change the log graph into exponential form before you start. So the base was A, the exponent was y, and the answer is x. So if I go here, it's going to become A to the 3/2 equals 8. Now, to solve that, we have A to the 3/2 equals 2 to the 3. To lose this, I'm going to raise both of those sides to 2. Doing that, I've got A cubed equals 2 to the 6. And to lose that, I'm going to cube root both sides. So A is equal to 2 squared. So A is equal to 4. So A equals 4. Which means I can now write this equation out as y equals log to the base 4 of x And we're now ready to go on. Now the good news is they've helped us out a bit here. They've said if A is 4, so you know you're right now. I mean, there it is reinforced for you. But that's quite useful that if you weren't able to do it, you were actually in a position to move on from there. Now it says determine the value of B if that's the point. Again, I'm going to go to this expression 4 to the y equals x, and I'm going to substitute this point in. So doing that, I've got 4 to the negative 2 is B, and therefore B is equal to 1/16. Nice and straightforward, no real problems. The inverse of the graph above is translated up by 2 units and then left by 1 unit. Give the new equation of the graph. Now that's not very hard to do, so let's quickly do this. We know that what's going to happen is it was actually y equals log to the base 4 of x. They tell me it's translated up by 2 units, so that means it would have become y equals log to the base 4 of x plus 2. That would shift it up the 2. And then left by 1 unit, so left by 1 unit impacts on this x value, and left by 1 unit means it would be x plus 1 plus 2. And there's your new graph ready to go. Anyhow, I really hope you've enjoyed being with us today, and you've got to see how this all works. Inverses will come into all sorts of sections. You'll suddenly find one in the middle of any graph that you're doing, and often with things you haven't seen before. But the secret is to remember it's just a simple reflection. So I hope you've enjoyed being with us, and please join us again. Thank you very much.